All right. We have edge of a cube is increasing at a rate of 0.05 centimeters per second. In terms of the edge of the cube S, what is the rate of change of the volume of the cube in cubic centimeters per second? So we ultimately are looking at a related rates problem. We have this cube that's getting larger. The edge length is increasing, in which case the volume would also be increasing. And we know that if we have a cube, that the volume is going to be length times width times height. But for a cube, all the dimensions are the same, so the volume would just be s cubed then. All right, and ultimately, again, we want to know what is the rate of change of the volume. Okay, and so that would be our dv dt, which we can find by differentiating our equation with respect to time. So we get 3s squared ds dt. All right, and ultimately this is dv dt that we're looking for here, 3s. We don't know a particular s. They didn't give us an instance at this point, but we do know ds dt is 0.05. So if I do 3s squared times 0.05, I get, not a calculator problem. It's 3 times 5, 15. So 3 times 5 is 15 at 2 decimal places, so it'll be 0.15s squared. And that would be an expression for our ds dt, or dv dt, which corresponds with letter D. What else? 15 through 30. Did we do that one yesterday? Yeah. Say that looks familiar. What else? We have a linear function piecewise. Got a bunch of line segments there. And it says that our g of x function is defined as the area from 0 to x of f of t dt, and f being the picture that we were given. So the question is, which has the greatest value? So if we go through and find these values, g of -3, and again we're looking at a bunch of line segments here. We got 0, 1 as a point, -3, 3 as a point. Going down here, and then we're going from there to 1, 2, and then down here to 5, -2. So that's essentially our picture. And so if we're going to go g of -3, keeping in mind that our starting point here is 0, everything's from 0. If we were to go back to -3, we'd have a trapezoid essentially. And so we'd have 1/2 times the height of the trapezoid would be 3, of course. The two bases would be 1 and 3. So 1 plus 3 in there. Ultimately we'd get 6. Now remember though that this is above the x-axis and we're going left, so it's not 6, it's actually what? It's -6. So that value is -6. What about g of 0? G of 0 is 0. Okay. G of 1? If I go from here to here, get that trapezoid, if you will. That's going to be 1/2 times 1 times the two bases are 1 and 2. So we'd ultimately get 3/2. So that's that. G of 3. We would have 3/2 for this part, and then if we add this triangle to it, which is a 2 by 2 triangle, so it'll be 1/2 times 2 times 2 would be 2. So ultimately it would be 2 plus 1/2, so 3/2. And then what's going to happen at g of 5, we're going to get some more negative area added to it. It's going to be less than this, so the question is which has the greatest value. It's going to be this one right here. And you can think about it from a little different standpoint as well. If this is our f function right here, and f is defined, the integral of f is g, then isn't f the derivative really of g? If g is the antiderivative of f, then wouldn't f be the derivative of g? So if we're looking at a picture of the derivative here, this point that we're going to claim is the answer, the derivative is equal to 0 there. Would it make sense to have a maximum here, possibly? And does the derivative go from positive to negative at that point? Again, from that standpoint, is it surprising that that's the right answer? What else? Anything else 16 through 30? Justin?
I just need help reminding how to do 27, like where I'm supposed to start off at.
So is the best graph. The graph best represents the position of the particle s as a function of time if the particle's velocity and acceleration are both positive. So remember, the velocity would be the derivative of our function that we drew. And so if you look at the choices that we have here, which of these, again, keep in mind if this is a position graph that we're trying to pick off here, if the velocity is positive, it needs to be increasing. So still in, still in, still in, still in, nope, still in. So these three are the only ones. And what do we know about acceleration? Acceleration is the second derivative. And if we want the acceleration to be positive, it needs to be concave up. So concave up. No, not concave up. Concave up. Nope. Concave up. So this one, since it's increasing in concave up, both the first and second derivatives will be positive. So that's why it's C. What else? 25. 25, we have graph. Another graph given. Says the graph is a differentiable function f as shown above. The graph of g is defined. So again, we have another area function here. So we're going from -2. And this is our g function of f of t dt. All right, and the question is, how many points of inflection does the graph have, the graph of g have, in the interval -2.5 to 5.5, which is ultimately all we can see there. Okay? So just in general, whether we're given equations or data tables or graphs or whatever the case may be, the bigger issue here is if we want to know inflection points for g, right, what do we need to know about g? When is g going to have inflection points, or when is any function going to have inflection points? Right. So what is the derivative then of g here? Close. F of what? X. It's the integrand evaluated at the upper limit. So first part of the fundamental theorem. So that's the derivative. Then what would the derivative of that be? The second derivative of g, if you will, would be what? F prime. And so that's essentially what we want to know is, when is f prime equal to 0? Like, that's when we're going to have inflection points. True? So if we have a picture of f in front of us, and again, we might have an equation, we might have a data table, we might have a graph, whatever the case may be, we still need to recognize that this is all we're after here. When is the second derivative, which is the first derivative of f, when is that equal to 0? So we have a picture there. It looks like our derivative equals 0 at 1, 2, 3 different points. Got 2 minimums and a maximum. Okay. So the derivative of that picture equals 0 3 times. So 2 minimums and the 1 maximum. So therefore, the answer should be B. Okay. And again, one thing I'd be a little bit careful is not only does the derivative equal 0 there, but the derivative changes sign, doesn't it? Goes from negative to positive, goes from positive to negative, and then negative to positive again, indicating that the second derivative changing signs, that is an inflection point. One thing I'd be careful is if that picture had something like this, like that would be 1, of course, right? And if it had, say, a flat spot like that, and then at that point right there, even though the derivative would be 0 there, is it an inflection point? The derivative goes from positive to positive, so that would not be an inflection point, would it? It'd be a candidate because the derivative equals 0 there, but does the derivative change sign? No. So therefore, the second derivative doesn't change sign either, and therefore it would not be an inflection point. So, and this one's pretty cut and dry because you just had 2 minimums and a maximum. So, but if you have a flat spot, that's not necessarily going to be a inflection point for the original function. Other 16 through 30.